let's start off with a couple of practice problems on naming. So I want to take a look at this very ugly alkene that I drew up here. Okay, that's a little bit prettier. We can count the number of carbons, 1, 2, 3, 4, 5, 6. We know the root is hex. We see an alkene, which means that the suffix is -ene. But actually we see two alkenes, which means we'll need to have a multiplier in there. This is going to be a diene. And I'll need to describe the positions of both alkenes before I say diene. I'll need to describe stereochemistry, if there is any. I'll need to describe if those alkenes are E or Z. And I'll need to clarify at what position it's E and at what position it's Z as best I can. And then I would have to name any other substituents. No other substituents, luckily, right? Now, the nomenclature that we would have given if there was just one alkene, we would have called it hexene, and maybe like hex2ene. But as soon as you need to add a multiplier in there, the nomenclature, like syntax, the rules changes a little bit. So it's going to bring hexa back in, even though the A at hexa is, we should associate it with hexane, and that means it's a part of ane, which is not a functional group. That's of priority here. So you might see this named one of two ways. First of all, whether I number from the left or from the right, I'm going to have my alkenes at position 2 and 4. So this becomes hexadiene. But you might also see it as hexane diene, where at that point they just name the alkane chain and then tack on this whole suffix that has the diene. And we're at positions 2 and 4, hexadiene, or I could do hexa 2,4-diene. And again, down here, 2,4-hexane-diene. But I haven't yet described the stereochemistry. I have both an E alkene and a Z alkene. So how do I decide whether my E alkene is at position 2 or my Z alkene is at position 2? Because remember, approaching it from either end, I get an alkene at the same positions. I'll need to say whether it's 2E or 4E. We're just going to alphabetize E and Z in the nomenclature. And since it's a tie either way, we'll also chronologically organize or numerically organize with the alphabetical order. So we'll say 2E, 4Z, 2,4 hexadiene. I don't think anybody would be confused if you said EZ, but it's just not as redundant as possible. Because in this case, it doesn't matter which direction you come from, you'll always get one E and one Z, always at position 2 or 4. But the best way would be to say 2E, 4Z, 2,4 hexadiene. Now, in rings that are smaller than 8 carbons, alkenes cannot afford the angle strain of being trans. The alkenes always must be cis in order to accommodate their bond angles. Until you get a ring that's more than 8 carbons long, and then you can have cis or trans alkenes. So in these 6-membered rings and 5-membered rings and 4-membered rings, we don't have to say whether the stereochemistry of the alkene is E or Z, because it's always locked in a Z configuration. And in a ring, I don't have to describe where the alkene is, unless there are two alkenes or a higher order priority functional group like an alcohol. Since the alkene is the highest priority functional group, I can just call this cyclohexene. But I need to describe where the substituent is. It's not just methyl cyclohexene. It can either be 2-methyl cyclohexene or 1-methyl cyclohexene. So I'll choose the lowest locant set. And the correct name here is 1-methyl cyclohexene. You could be even more redundant and say 1-methyl 1-cyclohexene. 1-methyl cyclohex 1-ene. It's not wrong, it's just more than what is commonly given. Now these names are incorrect. 4-methyl cyclopentene and 1,1-dibromo 2-methyl 4-pentene. So let's draw them out and figure out why they're incorrect.
Why is the alkene not numbered 1, 2?
It's the highest priority group.
So shouldn't the highest? I thought, didn't you say the highest priority should have the lowest?
That's right. And since it's a ring, where do I start? At the alkene carbon.
Yeah.
So
why
it's
is
the
it
highest
2
priority?
instead of 1?
The alkene's not at position 2. The alkene is at position 1. It is also position 2 because we count through an alkene.
So why is it 2, 4?
Because there are 2 alkenes. 1 at 2.
Oh, that's not.
1 at 4.
Never mind. I thought that was a
Naming for this
yeah,
one.
Yeah.
No, that's my bad. That's why I tried to draw this box around it.
I didn't even notice you do that. Okay. Got it.
So 4-methyl cyclopentene. Here's my ring. It doesn't matter where my alkene is. But now to get to position 4, I must count through the alkene. So wherever I decide to call position 1, whether here or here, I have to count through the alkene. 1, 2, 3, 4. I apologize. I thought that name was going to be wrong. That's not what I was going for. Anyways, that name is correct. Because you number it the other way, 1, 2, 3, 4. There is no better way to name it, 4-methyl cyclopentene. So I guess I was actually thinking of giving you 5-methyl cyclopentene, which 1, 2, 3, 4, 5 would end up here. And a better name would be 1, 2, 3, 3-methyl cyclopentene. So that's my bad. I apologize. I didn't proof that well enough before I gave it to you. What about this next one, which I know for a fact is not best? 1,1-dibromo 2-methyl 4-pentene. So doesn't matter which side I pick. I'm going to put my bromines over here. 2-methyl, 1, 2, 3, 4-pentene. So the alkene goes this way. What's wrong with this name? Not necessarily start with the alkene. And the confusing thing about that is when people hear start with the alkene, they come back to this one and they say, this is carbon 1 with a methyl substituent, 2, 3, 4, 5 carbons long. So you don't need to start with the alkene. But what you want to do is give the alkene its lowest locant set. So I'm going to start from the other direction. 1, 2, 3, 4, 5. Keep in mind that my first locant set was 1, 1, 2, 4, And by numbering this way, I now have a locant set of 1, 4, 5, 5, which you guys can see is not the lowest locant set. So what? This is the locant of the alkene. This is the locant of the alkene. This is what we're actually comparing. We prioritize the alkene hitting its lowest locant. And that happens when we number this way. The rest of the compound, its locants will be what they are. Does that sound okay? So we're kind of changing the game from the first time we looked at nomenclature. We're prioritizing certain functional groups all the way through. So a better name for this would be 5,5-dibromo, 4-methyl pentene. No. 1-pentene. The only time I can assume the position of an alkene is if it is in the ring and it is the only high priority functional group. Okay. Good review on nomenclature from our last class. No one's concerned that I didn't name the stereochemistry of this alkene?
It's really quick, so we wouldn't start with like the alkene in like a linear, but with a ring. Should we start with the alkene group?
Yes.
Okay.
So where do you start in a ring? Anywhere you want. Well, where do you want to start in a ring? At a high priority functional group.
Mm-hmm.
So here and here, I have to start at the ring. Or sorry, I have to start at the alkene. Especially since the alkene locant isn't even named.
Mm-hmm.
The reason it's not named is because it's assumed you're going to start there.
Gotcha.
That's the rule. Start at that high priority group. But in a chain, don't start at an alkene. Find the longest carbon chain that includes an alkene. Here that means starting at the alkene, but not always. And anybody concerned that I didn't name the stereochemistry of this alkene? There is no stereochemistry. It has a CH2 group, so one of its carbons has 2 identical groups, no stereoisomer. All right, there's one last small thing about this nomenclature that I want you to have, which is the methylene group. So this compound is called methylene cyclohexane. Methylene is a substituent of cyclohexane. That's what the name is saying. And methylene means 1-carbon alkene. Can you have a 1-carbon alkene? No. An alkene needs 2 carbons, so how do you have methylene? Okay, well, it's not technically cyclohexane either, because one of the carbons is sp2 hybridized, but I can't name a parent chain that includes a carbon inside the ring and a carbon outside of the ring. And this molecule does exactly that. The alkene spans inside and outside the ring, which means there is no parent chain that includes the alkene. So I have to name the alkene kind of as a substituent. So methylene, we've actually used that word before. Do you remember? Very early on in the semester, we were learning about regiochemistry of carbons, degrees of substitution, and we said that anytime you have a CH3 group, we call it methyl. Anytime you have a CH2 group, we call it methylene. Anytime you have a CH group, we call it methine. And that methylene is what we're looking at there, that CH2 group substituted off of cyclohexane. All right, you're not going to see that a lot, but I just want you to have some awareness of it in case it ever pops up. Last week, we were looking at MO theory of alkenes. We actually saw how that told us that the pi bond in an alkene is what governs reactivity. And so what we're going to do right now is segue from section 7 on alkenes into section 8 on alkene reactions by looking at the reactivity of alkenes. In fact, we're going to look at the synthesis briefly and reactivity briefly of alkenes. This is going to be a reaction we spend a lot more time on in Unit 5, so next week. We're going to be able to synthesize alkenes by eliminating alcohols. And we're going to learn a lot more about this, but for an example, this molecule is 1,2-dimethyl cyclohexanol. And we're going to react this with acid, H2SO4. And the major product that forms is 1,2-dimethyl cyclohexene. This is an elimination reaction. So the OH left. What else left? The OH left and a pi bond formed. But what else left in order for that pi bond to form? A hydrogen left. Overall, OH and H. Water. So this reaction, elimination of alcohols, this is referred to as dehydration. Now, I think you guys would agree it's this hydrogen that left. Let's sketch it in. It's that tertiary hydrogen that was removed with the OH in order for that pi bond to form. If we used some descriptive terms like alpha and beta, we could say that this is the alpha carbon. It has the alcohol. Any carbon attached to that is a beta carbon. Beta, beta, beta. There are 3 beta carbons for that tertiary alcohol. And one of them was involved in the elimination reaction. Which one? How can you describe the beta carbon that was involved compared to the other beta carbons? Use its degrees of substitution. The tertiary beta carbon went through elimination. The secondary beta carbon did not. The primary beta carbon did not. So what we're seeing is regioselectivity, or a regio preference. The most substituted beta carbon reacted, which means the most substituted alkene formed. And what do we know about the most substituted alkene? It's the most stable. It sits at the lowest energy. Now, to be fair, in organic reactions, it's very rare that you ever have just one product that forms. So this forms at maybe 90%. We call this the major organic product, but we also likely formed those 2 other alkenes as well. So for instance there, I have 1,6-dimethyl cyclohexene, and the other one I have 1-methylene 2-methyl cyclohexane. And they just form to much, much smaller amounts. They're considered minor products. They're not going to be the ones that we focus on predicting. But it's all regiochemistry. And they all just are formed by slightly different variations in a reaction mechanism. All right, there was something else I wanted. I wanted to demonstrate for you. If we look at this, we basically have the same starting material, the same activation energy. I mean, to be fair, actually, there's a reactive intermediate that forms here. So we're just looking at a reaction coordinate diagram. The starting material turns into a reactive intermediate. And then of these 3 different products, they all sit at different energy levels. So which one is most likely to form? The one that is the most stable. What else is likely to form? Decreasingly so, the ones that are less stable.
So these are not resonance structures, these are potential products.
Someone else want to answer that? Are these resonance structures? Are these resonance forms of the same molecule? What do resonance forms differ by? The placement of pi bonds or pi electrons. Is the only thing that's changing here pi electrons and pi bond placement? How many H's at this carbon? 0. How many H's at the same carbon in this product?
1.
And here? 1. So, are they resonance structures? No. They are structural isomers. Great question. Good review.
So you said the first reaction was dehydration.
That's the reaction we're looking at, yes.
Does that apply, does dehydration imply H2O as a byproduct?
Dehydration
I'm
implies
wondering what the
H2O
difference
as
of
a byproduct.
dehydration and dehydrogenation is.
Dehydration, hydrate or dihydrate, water. Dehydrogenation, hydrogen.
So
Remove H2.
that OH was a methyl group, it would be dehydrogenation.
If that OH was a methyl group, then nothing would have happened. If you go from an alkane, only seeing H in the molecule, to an alkene, then you have removed 2 hydrogens, H2. That's dehydrogenation.
That's really what I was wondering.
Yeah. We won't see an organic synthesis that allows us to do dehydrogenation. It's incredibly difficult. Enzymes have mastered it. Biochemistry has mastered it. Organic chemists have a more challenging time with it.
So is the sulfate not present because the hydrosulfure donated protons?
So actually the H2SO4 is acting as a catalyst. It's neither consumed in the reaction nor produced by the reaction. It does act as a proton source, but it also acts as a weak base. The reason that there's no SO4 group or SO4H or whatever in the product is because it's also a bad nucleophile. It doesn't look to form bonds. So it is just acting as a catalyst thing.
So could you add like right next to H2O SO4? Or would that,
Sorry, one more time.
like, could you add the SO4 next to the H2O parentheses since it hasn't been consumed?
Yes and no. But actually, if you just look at the stoichiometry, then you can see that there's HOH, H2O. Everything is balanced. The H2SO4 is not being consumed in any way. And we'll talk about this again more next week.
So going back to this A, B, and C, would it be fair to say that you could replace the plus signs with or? So you could have this, or this, or this, but your likelihood of getting A is this much higher.
In reality, you are getting all of them.
Okay. But the proportion is much higher for the lower energy state.
That's correct. Yeah. You form much more. That's your major product. You form much more of the most stable product.
You're getting all of them.
You
but
get
in
like,
proportions.
let's say you get
99%.
a mole of starting material, you expect a mole's worth of products, but you get 0.9 moles of this, 0.09 moles of this, and 0.01 moles of this. So that's like 90%, 9%, 1%. When I was in grad school, I TA'd the organic labs for CU Boulder, and they had a dehydration experiment. We actually took the product mixture to the NMR, and at the NMR, we could see different hydrogen signals. It wasn't this reaction, it was something similar, but all three products had vanillic hydrogens, alkene hydrogens, and all of their signals showed up at different regions, so we could identify all of those signals, and then we could actually integrate them and figure out there's 90% of the most major product, and 10% of the less major product, and less than 1% of the most minor product, using quantitative NMR analysis. Very cool, but not possible here with our instrumentation.
Can you repeat how do you tell which is the most stable?
Yeah. How can you describe this alkene, Cameron? This alkene has what degree of substitution? And you're not going to use primary, secondary, tertiary, quaternary, because that describes carbons. Alkenes are 2 carbons. So you're going to use mono, di, tri, tetra.
So that one on the lower would be tetra.
This is tetra substituted, which is why it's the most stable. What is this?
Right.
That's right. And this?
Di.
Di substituted. Tetra, tri, di. Those are the decreasing order of stability.
So C is di because there's just the carbon or the double bond.
Well, I've got 2 hydrogens, 2 carbon groups.
Oh, okay.
Di substituted. 3 carbon groups, tri. 4 carbon groups, tetra. Good. All right. The other way that we can form this is by elimination of alkyl halides. Now, with alkyl halides, things get a little bit more complicated in terms of regiochemistry and reagents. So I'm just going to leave this now to say base. Rather than acid, we need a base for this elimination reaction. Your starting material functional group dictates what reagents you need. And the product that we're going to get here is cyclohexene. The bromine has been eliminated, correct? What else has been eliminated? A hydrogen. So if I remove a hydrogen and a halogen, I could call this elimination dehydrohalogenation. And Brett, in that word, we're saying hydrogen and halogen being removed. Now, you could argue that there is a byproduct of HBr, but that would imply that the base is acting catalytically, that the base is not being consumed, and there is very few bases that can exist as a base in the presence of such a strong acid. So here it would actually be better to say that the product is H base plus balanced by Br minus. The base has become a conjugate acid, Hb plus. And the bromide is just acting as a counter ion. But that shows, either way you show it, it shows that the H and the Br have been removed. So we're going to dive into elimination reactions more next week. We're going to talk more about their regiochemistry. We're going to talk more about their stereoselectivity. But this is just our setup for now. If you don't have an alkene in a molecule and you want to react with an alkene, you can make an alkene. Next, we're going to look at reactions. We're going to look at alkenes reacting as bases. They can also act as nucleophiles. Base is a little bit vague, right? But to be fair, In the versions where they act as nucleophiles, from my perspective, they also act as electrophiles in the same instance. So there are really instances where they act as bases in the presence of an acid, Bronsted-Lowry acid-base stuff. So I'm going to give you an example. Take, for instance, propene reacts with H+. What's providing that proton? Maybe it's HCl, maybe it's HBr, maybe it's H2SO4. I would say it's H3O+, but I do want you guys to realize that H3O+ only exists in the presence of something else like HCl and water. So you have H3O+ and Cl-. Or H3O+ exists if you have H2SO4 and water, in which case you have H3O+ and HSO4-. So any acid environment, this forms. Tell me the change that's happened. Addition, fair, although typically we look for two things being added, and the second thing hasn't been added yet, just one. I heard somebody else. Good, pi bond consumed, which kind of hits on our addition again. Addition of hydrogen, the hydrogen has been added. Give me more detail. It gained a charge. We can say there's conservation of charge, right? Reactants are net positive, product is net positive. What did you say? It formed a cation. Technically, the cation changed positions, but we can actually name this cation. I think we have named it already. This is a carbon cation, so it's nicknamed carbocation. And I hear this a lot. People read that word, and it looks like it ends like vacation, so they read it as carbocation. But that's a carbocation. It's such an important ion that we're going to refer to it as a carbocation. Be more specific about what's happening.
Has it become less stable?
Hard to say if it's become less stable or more stable. It probably is reactive, yes. So it probably is less stable. I think it's fair to argue that.
Is it because like that terminal gains that hydrogen, so the electrons are delocalized in the center?
That's what I want to hear. Well, okay, we can talk more about how the electrons are delocalized, but what I wanted to hear was where the hydrogen added to. Did you have something you were saying?
Just say it's an addition reaction.
Okay, yep, it is an addition reaction. So if we draw this out, the CH2 group becomes a CH3 group. The CH group stays a CH group. So the hydrogen adds to the less substituted carbon, which means that the less substituted carbon acts as the base. So that means we can actually draw a reaction arrow. I can take the pi electrons and draw them to the H+. But does the reaction arrow really tell me which carbon is using the electrons and which carbon is losing the electrons? It does not. Only the product shows me that. You guys remember that from your midterm exam. So we can take something away from this. we can say that this carbon is more negative and this carbon is more positive. Less substituted, more negative. More substituted, more positive. What we will never see, and I'm gonna indicate that we never see that by putting an X through this arrow, not seen, is the formation of this less substituted carbocation. Doesn't form. What we're doing right now is learning something about the regiochemistry of carbocations. When given a chance between two carbons of different substitutions, carbocations have a preferred regiochemistry. Carbocations prefer more substituted carbons. I'm going to abbreviate carbocation as C+.
So would carboanions have an inverse relationship?
That's true. Carbanions have the exact opposite relationship. Carbanions are more stable on less substituted carbons, less stable on more substituted carbons.
Is that something about like it just wasn't really, really tiny or just at all, ever?
At all.
Okay.
It always has a preference for the more substituted.
Okay.
Good question. Are these two starred points, are they saying different things? The less substituted carbon acts as the base, the more substituted carbon forms the carbocation. That's saying the same thing, just from different sides of the reaction arrow. Less substituted carbon is basic, the more substituted carbon better holds a positive charge. That's why the less substituted is more basic, because the more substituted is better at holding a positive charge. Okay, so to kind of sum this up, I want to show you guys 3 resonance forms of propene. One, where the electrons are taken by the less substituted carbon, and one where the electrons are taken by the more substituted carbon. All we're saying is take the pi electrons, delocalize them. Or, take the pi electrons, localize them to one carbon or the other. Which of these is the most stable resonance form? The most major contributor to the molecule? The one in the middle. It has minimum charges. But what's the next major contributor that helps predict the structure? The one on the left. So of course this is our major, but the one on the left says this has a stable carbocation and it has a stable carbanion. And this is what feeds back in to tell us partial positive, partial negative. And remember, when a bond breaks, the bond is taken by the more negative atom. It leaves a positive charge when a bond breaks on the more positive atom. Okay, so this is an example of an asymmetric alkene. And the asymmetric alkene has regio-specific character. But what happens if I have a symmetric alkene where both carbons are equally substituted? Which carbon takes the electrons? Which carbon loses the electrons? There's no way to know. The carbons have the same substitution. They're connected to the same number of carbons. Then we can call this regio-random. Both carbons are likely to act as the base. Both carbons are likely to lose the electrons. Maybe not equally likely. Maybe it's 60-40, maybe it's 70-30, but it's not all or nothing. So asymmetric. What we're not saying here is chiral. What we're saying is the carbons have different degrees of substitution. Symmetric. The carbons have the same degrees of substitution, even if the carbon chains on either side are not the same. There's no symmetry in the molecule necessarily, but they have the same degree of substitution. So I can put, again, partial negative, partial positive, but up here, it's more like partial question mark. They can both take the electrons, they can both lose the electrons. You okay with that? So this leads to a guy's, you got a question you want to ask? Okay. This leads to a guy's rule. Markovnikov's rule on addition regiochemistry. Marx said in alkene additions, actually, I mean, I do think that he was specifically talking about alkenes, but let's just say that in additions, Markovnikov said that H adds to the carbon with more H. And that earned him his PhD back in like 18th century Germany. I don't like it. I don't like that rule. It's not good. Because it doesn't explain anything. If anything, it makes you think, oh, well, a carbon that has H's wants more H's. So that carbon just takes more H's. There's absolutely no reason for it. Instead, we can actually see, oh yeah, the carbon with more H's does take the H. That's Markovnikov addition. But it's because that carbon is more negative. But you guys are just kind of trusting me when I tell you that carbon is more negative, and that carbon is more stable when it holds a negative charge, and that the more substituted carbon is more stable when it holds a positive charge. So what I'll give you then is an energy diagram. And on this energy diagram, we're going to show different carbocations. At the very top is a methyl carbocation. This sits at the highest energy. It holds a positive charge and it has hydrogens all around it. At the next level, we'll have a primary carbocation. Now, I don't want to get it too messy and cluttered in here, but that methyl group, that primary carbocation, it is actually able to receive electron donation from neighboring groups. I call it moral support. Those electrons come in and sterically support, electronically induce the positive carbon, which makes that positive charge a little less positive. This process is actually called hyperconjugation. You guys might remember that we learned about conjugation in the context of resonance. Hyperconjugation sounds like it's resonance on steroids, but it's actually not quite resonance, so I feel like it should be called hypoconjugation. It is neighboring electron pairs that are donating into an empty p orbital on the carbon. If I take this to a secondary carbocation, I can now have hyperconjugation from both of those neighboring groups. That protects that positive charge even more. That makes that positive charge even more stable. And then, of course, if I take this to a tertiary carbocation, I get hyperconjugation from all directions. And I am showing this only with hydrogens, but to be fair, it could be a carbon-to-carbon bond. It could be a carbon-to-oxygen bond. It's just neighboring electron density that is flowing in.
Is this the same idea as induction then?
It is induction. It is that electron push. And how much can hydrogens push electrons? Well, they don't have a lot to push. But what about 3 other carbon groups? Those have a lot more electrons that they can push. So this is a methyl carbon, primary, secondary, tertiary carbocation. And if we imagine that they're all coming from the same starting material, which of them would be the easiest to form? The lowest energy one. The one that requires the smallest activation barrier. So tertiary carbocations form very easily. Secondary, somewhat easily. Primary, not very well at all. Methyl, very challenging to form. So let's take this back to our asymmetric alkene. Which carbon is more likely to take on a positive charge? The more substituted carbon. And we can actually reverse this for the carbanions. A methyl carbanion is the most stable because the carbanion has a lone pair for itself. Lone pairs cause electron repulsion. So you want to have the smallest amount of neighboring electron density when your carbon holds a lone pair. You put a lone pair onto a tertiary carbon, and it experiences electron repulsion from all of these groups. Back in section 2, back in unit 2, we learned about conformations of molecules, and we said that eclipsed conformations experience electron repulsion. This is basically that same eclipsed conformation, except now there's not a lone pair or a bonding pair. And so that conformation helps to stabilize the positive charge. Hyperconjugation is the same orientation that we think of torsional strain happening from, but you lose that other bonding pair of electrons. So you lose the actual strain, and what you get is stabilization. All right? So this is ranking carbocations. Markovnikov recognized a pattern. Hey, when I do all these addition reactions, the H always goes to the less substituted carbon. And then we have a number of reactions that we're going to learn this semester that we'll call anti-Markovnikov, because the H adds to the more substituted carbon. And it's all predicted by charge stabilization. All of it is predicted by charge stabilization. So maybe it's convenient to be able to say, like, hey, 8 of these reactions go this way, the other 2 go that way. But I don't want you to just fall in line with Markovnikov because his name is written in textbooks. His rule doesn't make any sense. His rule is just an observation of carbocation stability. And he just never realized carbocations were in there. Deal? Okay. Why don't we take a quick break? And when we come back, we're going to look more at these types of reactions. I'm bummed because I had my camera tilted the wrong way and it didn't get the right-hand side of the screen earlier.
It actually slid down and fell.
Oh, so maybe it did get the screen earlier?
I think it did earlier.
Oh, good. Before I erased it?
Randomly out of nowhere, it just kind of dropped down one level.
Okay, well, I'm not mad about that. Makes it exciting.
Yeah.
I was thinking about redrawing what I had over there. But maybe it got it.
Yeah, I mean, it's I don't know if it rotated when it did that, but it just fell.
Mm.
Oh, like the middle resonance? Yeah. Isn't that basically just like the filled octet thing? Markov?
None of them have a filled octet.
No, but like, won't hydrogens be attracted to carbon that's closer to one its octet?
Will hydrogens be attracted to a carbon that has full octet?
Like almost a full octet versus rather like no octet, like no hydrogens. Like your carbon will have greater pull.
They all have the same number of electrons.
Right, but like you know how like when you're doing electronegativity, whichever one's closer to the its octet, like one more than the others. Does that play within this, or is it just?
But I don't understand because
Oh,
they
sorry.
all have the same amount of electrons.
Right. So it's just a substitution.
Yeah, but hydrogens aren't pulling on anything.
No, carbon.
The carbon can't pull on hydrogens on the methyl carbocation. There's no neighboring hydrogens. There's only the hydrogens it's bonded to, and there's no other electrons in the molecule that it can try to tug on.
Oh shit, that's true. So I guess it's like a way to describe why more hydrogens go to more hydrogens.
Hydrogen goes to the carbon with more hydrogen because it creates a carbocation. Hydrogen goes to the less substituted carbon
Oh.
so that the positive charge goes on the more substituted carbon. If I could reword Markovnikov's rule, I wouldn't say H adds to the carbon with more H. I would say positive charge adds to the carbon with more carbons, or the positive charge adds to the more substituted carbon.
Mhm.
Because that's what's happening.
Yeah. Yeah.
It has nothing to do with the H.
Yeah.
Markovnikov was trying to throw you off.
Right. No, yeah, that made me think about electronegativity.
He wasn't actually. There's another guy we'll talk about next week. His name is Zaitsev. And Markovnikov and Zaitsev were doing research at the same time, and Zaitsev was trying to get his PhD published on the work that would later be named after him. And Markovnikov was pushing for him to not get his PhD. Markovnikov was like, no, Zaitsev's work doesn't make any sense. Zaitsev's work was on elimination and the regiochemistry of elimination. So earlier when I had those alkene products, you could say one is the Zaitsev product, one is the anti-Zaitsev product. And Zaitsev's rule actually makes sense. I don't have anything to add to Zaitsev's rule other than it being named after him. But Markovnikov's, it's a dangerous road for me to teach, because if I try to explain why he's wrong, it just makes it more confusing than just following his trend. A few years ago, I tried actually like totally disowning Markovnikov and saying Markovnikov addition, and I would apply it to things that didn't even have H because it was all based on charge stabilization. But then students were like, what is Markovnikov, what is Markovnikov, and what is anti-Markovnikov? Since everything is based on charge stabilization.
So, like, does resonance, not resonance, does electronegativity change at all? Like, versus a full octet versus not, or is it always the same?
Which of these carbons has a full octet here?
None.
Good. So what does it have to do with a filled octet?
Oh no, I was just wondering, just in general. Like, if you had like a CH4 versus just a CH, the electronegativity would be the same.
Oh, you're going to electronegativity.
I was just like, it's pretty off topic. I was just curious.
Yeah, carbon always has the same electronegativity, no matter what it's bonded to, no matter what it is, what its formal charge is. It always has the same electronegativity.
And that's with isotopes too. It's always the same.
Actually, no, I don't know. Isotopes might have different electronegativities. All right, I want to summarize this one more time for us. Carbocation stability. Increases with substitution, but it also increases with resonance. And in fact, resonance plays a very important role in it. The thing is, in our class, we're not going to see resonance stabilization quite as much. We might in a couple of weeks towards the end of the semester, but the resonance stabilization becomes a big role in OChem 2. So if I were to say the least stable carbocation here on the left and the most stable carbocation here on the right, I'm just going to give us some examples of molecules because we kind of understand it increases with substitution. So over here I would have the methyl carbocation, CH3+. And here I would have the tert-butyl carbocation. That's a carbon with 3 methyl groups around it. And here I have a resonance stabilized primary carbocation. That carbocation is lower substitution, but it has increased resonance. So resonance actually plays a very big role in stability. Substitution is secondary to that. And then over here, what I would have is a tertiary benzylic carbocation. And those are some words I want us to be reminded of. Allylic carbocation, and benzylic carbocation. Allylic means adjacent to the alkene. So in this case, the carbocation is in resonance with the alkene. The carbocation is not in one place. The carbocation is in two places. Or it's delocalized. Why is benzylic so much more stable? Because the benzylic position is in resonance with the entire ring. It's delocalized over more carbons. More delocalization, more resonance forms, more stable.
You put pH in the erase state. It could be either.
Well, pH is short for phenyl, and phenyl is the benzene ring.
Yeah.
So the only reason I erased pH was in case you wanted to show the resonance forms. Now you're reminded about those double bonds within the ring. There's also this common trend I see in OChem 1 where students mistake the aromatic ring and cyclohexane a lot. So I just want to point out again that the pH, the benzene ring, it's got those double bonds. And those double bonds are what's responsible for resonance. All right. On this topic of carbocations, we're going to look at carbocation rearrangements. Carbocations will form at one alkene position or the other. But once a carbocation forms, that doesn't mean that it is the only carbocation that exists. Some carbocations form on a less stable carbon adjacent to a more stable carbon. Then the carbocation rearranges to become more stable. This process of hyperconjugation, that empty p orbital pulling nearby electron density, sometimes it pulls too hard and it pulls an entire group over to the carbocation, which leaves a hole in its wake, a new carbocation. And there's two common things that shift. We'll look at a lot of hydride shifts. That's where hydrogen and its electron pair moves over. Now I want you to think about that name, hydride, H-. That's what hydride means, negatively charged hydrogen. And that's because hydrogen is taking its electrons, which it doesn't own. Carbon owns the electrons. But it is taking those electrons and moving over to the carbocation, leaving in its wake a more stable carbocation. So let's take, for example, this alkene, 3-methyl-1-butene. When this reacts with H+, it's going to form only one carbocation. What will it form? Will it form a primary carbocation or a secondary carbocation? Secondary. Because a secondary carbocation takes less energy to make, is easier to form. But that secondary carbocation is adjacent to this tertiary hydrogen. So the secondary carbocation is pulling on that adjacent hydrogen. Keep in mind, it's also pulling on adjacent hydrogens from the primary carbons. But the carbocation is pulling on that adjacent hydrogen, and if that hydrogen were to leave, it would leave a hole on the tertiary carbon, which would be more stable. So what we see is the hydride shift. why is it that the arrows don't indicate anything about the positive charge? I don't start at the positive charge and point towards the other carbon. I don't look at the other carbon and point towards the positive charge. Do positive charges indicate electrons? Then how can an electron arrow start at a positive charge? It can't. So if you want to remember that this positive charge is going to move to this carbon, don't use arrows. I don't care what you decide to do, but you can't use arrows because that deceives a mechanism. You're mistaken about what that arrow is meant to say. What this is saying is the CH bond relocates to a different carbon, leaving in its wake a new positive charge. You guys okay with that? And why is it able to do that? Because bonds are not stiff, they're not stagnant. These bonds are vibrating by stretching. They're vibrating by bending. And so at some point, that hydrogen is going to bend a little bit too far and just relocate to the other carbon. If you want to think about electron orbitals, and I know all of you love to think about electron orbitals, your carbocation has what substitution, or sorry, what hybridization? sp2. Because it's only got 3 electron regions. That means that the carbocation has a p orbital. And that p orbital, it actually looks a little bit like the hybridized s to sp3 orbital of the adjacent carbon. And if those two orbitals just get close enough to bridge together, then the electrons can just slide over to the other carbon and leave this carbon empty of an electron pair.
But going back to an earlier topic, we wouldn't call this resonance because we're not dealing with pi bonds.
Correct. We're not dealing with pi bonds. This is not just the delocalization of pi electrons. There's an entire hydrogen that's moving.
And the hydrogen moving is what changes the charge.
Changes where the charge is.
Neutralizes one charge and creates a cation.
That's right. Yep. Satisfies the positive charge here, but creates a positive charge here by leaving with its electrons.
So resonance is only related to electrons associated with pi bonds.
Yep.
Kind of connecting through a circuit.
So either a pi bond electron or sometimes lone pairs.
Okay.
Lone pairs can be involved in resonance, creating pi bonds.
But because this involves a hydrogen, we're talking about like an isomer.
Structural isomerization, structural rearrangement. Yep, 100%. Oh, sorry, I didn't mean to put alkyl halide. Wow. The other one that we're going to look at is alkyl shifts. Now, the most common alkyl shift is a methyl shift. And here's really the only instance that a methyl shift would occur. A methyl shift occurs if there's no hydrogen that can shift to create a more stable carbocation. So in this case, oops, sorry, I forgot my double bond. If I take 3,3-dimethyl 1-butene, and I create this secondary carbocation, there's no hydrogen to shift over and create a more stable carbocation. But there is a methyl group that can shift over. I think you guys can imagine that that takes more energy to move an entire CH3 group than to just move an H. it moves the methyl group and it leaves in its wake a new positive charge. Yeah.
Is there not a hydrogen on the terminal carbon too? Why does it choose to pull the
Carbocations have to be adjacent, or sorry, rearrangements have to occur from adjacent positions. So I can't take a hydrogen from here, from this CH3, and bring it down. Although it,
like the rightmost CH3.
well, if I did take a hydrogen from there, it would leave a primary carbocation anyways, which would be less stable. And I can't take something from here. I can really only rearrange, or the molecule can only rearrange from an adjacent position. This is going to be one of the most common things. Hydride and methyl shifts will be the most common rearrangements that we'll look at. But I do think it's cool to look at ring expansions. Ring expansions occur especially when there is a very constrained ring, something whose bond angles are very tight. When these take on carbocations, the ring can actually structurally rearrange just by one position. It breaks a carbon-carbon bond in the ring, similar to how this breaks a carbon-carbon bond in the chain. So now carbons 1 and 4 are no longer bonded to each other, but 1 or 4 is now going to bond to this carbon out here. This gives me a new 5-membered ring that I drew very poorly, with just a methyl group coming off. If we were to map our carbons though, 3 to 6 is breaking, 2 to 6 is forming. Where is the positive charge? Carbon 2 had the positive charge. Does it still have it? No, because carbon 2 has accepted a bond from carbon 6. Carbon 6 had 4 bonds. Does carbon 6 still have 4 bonds? Yes, because carbon 6 broke its bond from 3, made a bond to 2. So who has lost a bond? Not carbon 1. Carbon 1's not really involved in any of it, actually. Carbon 3 has lost a bond. So the positive charge is now on this secondary carbocation. And what do you think would happen from there? There's a secondary carbocation adjacent to a tertiary carbon. So now this hydrogen on carbon 2 will go through a hydride shift. Multiple steps, okay? Like it's not just happening at the same time. First the ring expands and then the hydride shifts to create that tertiary carbocation. Notice that each time the shifts, the rearrangements are only happening adjacent to each other. That's it. All right? Carbocation rearrangements are going to be very important when we learn about reactions in section 8, because to be able to predict a product, we'll need to predict if it forms a carbocation. And if it forms a carbocation at a position that is adjacent to a more stable carbocation position, we have to be able to predict that the rearrangement will occur. In order to predict the right product, we need to be able to predict if a rearrangement occurs.
So it seems like a lot of what we're talking about is like these intermediates, and it's slowly settling down
Yeah,
to a lower energy.
that's right.
To where it's
And not
finally-
slowly. It is
Well,
like picoseconds type stuff.
okay.
bond vibrations happen very quickly, which means that these intramolecular rearrangements happen very quickly.
So we're like going to a state, and then we're looking adjacent to wherever we have this carbocation.
Yeah,
Is there a lower energy state that could exist?
Yep.
If so, then we move down one more level.
if a carbocation forms, consider if there is a more stable carbocation that could form adjacent to it. Exactly. All right. One of your unit test questions is on mechanisms, or excuse me, on carbocation rearrangements. And I like this question because it highlights understanding of the energy constraints around rearrangements. This will rearrange into a tertiary carbocation. But which direction will it rearrange? Will this go through a methyl shift or a hydride shift? What would take more energy? Methyl shift would take more energy. And what would provide more stability? The hydride shift would make a more stable final product? If the methyl shift occurs, what type of carbocation do I end up with? Tertiary. The hydride shift occurs, what kind of carbocation do I end up with? From here, hydride leaves, carbocation forms, tertiary. So in this molecule, both a hydride shift on the right or a methyl shift on the left would yield a tertiary carbocation. So we're saying from the starting material to the product, I either have to go through a big energy barrier or a small energy barrier. Which one is going to occur? The one that requires the least energy. That happens first. Hydride shift is favored here. I mean, if there's enough energy for the methyl shift to occur, then there is enough energy for the hydride shift to have already occurred, right? So if anything, you're going to get a mixture of both, but it's unlikely that you would get only the methyl shift. It's more likely you'll get only the hydride shift. Okay? Now, I do want to say carbocation rearrangements from alkyl groups to allylic positions or to benzylic positions, those are incredibly favored. Even if it goes from a tertiary carbocation to a secondary benzylic carbocation, that benzylic position makes it that much more stable. But we're not going to see that much this semester. So,
is least stable highest energy and most stable is low energy?
yeah, that's right. But I do want you to remember that just because this is the most stable and the lowest energy, it's still a reactive intermediate. So it's much higher than what the starting material or what the product will be. That just means that it being the most stable makes it the easiest to form, but very much so still reactive. So reactions with alkenes then, especially with alkenes as bases, let's consider the HX addition reaction, sometimes referred to as hydrohalogenation. I'm going to start here with just HX. I'm not going to say what X is, but it could be Cl, could be Br, could be I. And I'm not going to show us what the starting material was yet either. I just want to say, I want to take an alkene and make this 1-halo, 1-methyl cyclohexane. What alkenes could I start with? And we're actually going to consider more than one. Is it obvious to see where the hydrogen added? Not really. The hydrogen could have added to these CH2 groups, or the hydrogen could have added here. So there's actually more than one place where my alkene might be. My alkene might be this methylene cyclohexane. The H adds, because this is an acid, the alkene acts as a base, and the H adds to the less substituted carbon. The carbocation forms on the tertiary carbon, and that's where the halogen adds afterwards. What other type of alkene could I have as a starting material? Can you give me its IUPAC name?
I guess just cyclohexane, right? 1 cyclohexane, 1-methyl.
1-methyl cyclohexene. Sure, because the hydrogen will add to the less substituted position. The carbocation forms on that tertiary carbon, and then the halogen adds there afterwards. Remember, the whole header that we're underneath, if you go back up in your notes, is 3, alkenes as bases. How do I know for certain that the alkene is acting as a base here in a reaction with HX? Because HX is an acid, hydrochloric acid, hydrobromic acid, hydroiodic acid. They're all acids, which means I know that in all of these reactions, the alkene is acting as a base. And when the alkene acts as a base, it forms a carbocation. The only thing that we're learning is that the carbocation then reacts with the halogen itself to complete the addition reaction. All right, are there any other starting materials that could give me this product? What do you think, Hayden?
Couldn't it just be all of it? Like every position of the ring?
No, definitely not every position.
Then the other side of it.
I'll say for instance, this one will never form that product. We can agree that this would be regio-random. The 2 carbons of the alkene have equal substitution. So either one could form the carbocation, but which carbocation would rearrange? Neither of them. Neither carbocations that form would rearrange, so I would never get that tertiary alkyl halide. So this one is a structural isomer that certainly will not work. Now, I'm going to put a line here because this alkene can form that final product. These 2 alkenes will act regio-specifically because they are asymmetric. Less substituted, more substituted. Less substituted, more substituted. I'll always consistently get the carbocation on the same position. But this carbon is symmetric. This alkene is symmetric, which means both carbons could take the carbocation. If the carbocation forms here, it's secondary, surrounded by secondary carbons. No rearrangement. No stability gained by rearranging. If the carbocation forms here, which it has a chance of doing, then it will rearrange to the more substituted position. So there's like not even a 50-50 chance, but there's some chance that this forms this product. There's also a chance, a very good chance, a non-zero chance, that it gives us a different product as well, because it is regio-random in its reaction. It's not regio-specific. Do you guys see where this is coming from? Take the alkyl halide and try to figure out what possibilities are there for where H and where X added, even accounting for rearrangements that could occur. Yeah?
So on this second one in the column, could we move that double bond to the other side and it's essentially the same thing?
Here,
No, up one? No, up to the
Oh,
second
sorry.
structure, yeah.
here to here.
Yeah.
You
so-
can prove if they're the same or not by naming it.
Right.
Yeah, and both of them would be named 1-methyl cyclohexene.
Okay. So in that case, because everything's the same, it wouldn't be a different structure.
Not a different structure. Nope. Just drawn in a different conformation.
That would be resonance.
No, that would be
Sorry,
conformational.
I'm a little bit
That's okay,
resonance
that's okay.
obsessed.
That would be conformational
Oh, wow,
isomerism.
resonance.
All you're doing is just flipping the molecule over.
Okay.
They're identical to each other.
Gotcha.
Resonance looks like different structures, but are just bad approximations of one molecule. Resonance forms are not different structures. They're not necessarily identical either, but that's because they're all bad approximations. Okay, so we're going to go through a series of reactions over the next 2 days. HX addition, X2 addition, 3 types of hydration reactions, epoxidation, diol addition, and oxidative cleavage. There are a number of other reactions that we could cover as well. The only reason we don't is because the textbook that is chosen for us with our course lead doesn't cover them in this section, so we're just not going to go over it. There are more alkene reactions we're going to come back to in Unit 5. I want to give you guys the rundown of how we're going to cover reactions in the next 2 days, because I don't have enough time to really give you some of these. What I'm going to give you guys is a generic reaction. So for the example of HX addition, we would look at an alkene reacting with HX, and we'll look at how that gives us H and X across. So we'll just give a generic, because if you want to organize these reactions and study them, it doesn't make sense to always have a specific molecule, but it sometimes makes sense to have a generic example of it. Then we're going to go over the notes for it. We're going to talk about its regiochemistry. That means, is it Markovnikov, is it anti-Markovnikov, or does it not really apply? And we're going to look at its stereochemistry. That is, if it forms chiral carbons, are those chiral carbons linked to each other? Are the chiral carbons always anti-configuration? Are they always syn configuration? Or do chiral carbons form randomly? And in the case of HX addition, the stereochemistry is random addition. When chiral carbons form, they are not linked to each other. The chiral carbons do not form in any sort of order. That's going to tell us whether we form enantiomers or diastereomers. It's going to tell us how many products we actually make. And then we'll do some examples. So we'll do an example that highlights regiochemistry, and we'll do an example that highlights stereochemistry, if not both. There are 4 reactions. How many did I say you were going to cover? 8. There are 4 reactions of the 8 that you will need to know the mechanism for by this weekend. And I'm actually going to go through those mechanisms at the end. So we're going to cover all the reactions, and then we're going to come back and review those 4 reactions. 2 of them are actually very similar, or there's 2 sets of 2, I should say. 2 of the reactions involve acid-base protonation steps at the start and carbocation intermediates. They're very similar. And 2 of them involve electrophilic ring-forming intermediates, followed by a ring-opening step. They're very, very similar. So there's really 2 types of mechanisms I'm going to have you learn. I'm not asking you to learn the other ones, not because they're too challenging or they're too hard or I'm trying to go easy on you, but because I think that if you can master these mechanisms, if you can really understand what's going on, you can apply your understanding of reaction mechanisms to any other reaction. You can make any other mechanism make sense if you master these 2 types. Does that sound good? If you want, I can make it so that we have to learn all of them, but I prefer this method. All right? And then as a reminder, your homework and your unit test is going to question you on, given 2 of the 3 components here, can you predict the 3rd? In addition to that, for those questions or for those mechanisms, those reactions we're learning mechanisms for, your unit test will have questions on which intermediates are involved in the reaction mechanism. Okay? It's going to be fun. I'm going to give you some tips and ideas about how to organize all this stuff too to study it better. So, see you guys tomorrow. Happy studying.